Hello everyone and welcome. This is Zen Programmer here. Today we're tackling a topic that's fundamental to every data scientist's toolkit: overfitting and underfitting. These aren't just buzzwords, they're challenges that can make or break the success of our models. We're going to explore what they mean, why they matter, and how we can strike the perfect balance between them to create models that generalize well. Let's start by defining these two terms. Overfitting happens when our model learns too much, not just the patterns in the data, but also the noise. Think of it like memorizing answers for an exam instead of understanding the concepts. It works great in the short term, but falls apart when faced with anything new. On the other hand, underfitting is when the model is too simple. It doesn't learn enough to capture the relationships in the data. It's like showing up to an exam with just a basic idea of the subject. You're bound to miss the mark. Our job is to avoid both extremes and find that sweet spot where our models learn just enough to generalize well. So, why do we care about overfitting and underfitting? Because these issues directly impact the performance of our models, and by extension, the decisions we make using them. Imagine a credit scoring model that overfits. It might predict perfectly for training data, but fail miserably with new applicants, leading to risky loans. On the flip side, an underfitted model might reject good applicants because it fails to identify important patterns in their data. This is why creating reliable models that generalize well is critical. It ensures our predictions hold up in the real world. At the core of all this is a concept called generalization. This refers to a model's ability to perform well on unseen data. And generalization is heavily influenced by the bias-variance trade-off. High bias models, like simple linear regressions, often underfit. They're too rigid to capture the complexity of the data. High variance models, like very deep neural networks, tend to overfit. They're too flexible and end up memorizing noise. Striking the right balance between bias and variance is like walking a tightrope. It's all about finding the equilibrium where our models perform well on both training and test data. Here's what overfitting looks like. Notice how the model matches the training data perfectly, even capturing tiny fluctuations or noise. But when tested on new data, it performs poorly because it learned the noise instead of the true pattern. It's like using a GPS that remembers every traffic detail from the past but fails to adapt to today's conditions. This is why validation is so important. It helps us identify overfitting early. Now let's look at underfitting. This happens when the model is too simple to capture the data's complexity. Imagine trying to use a straight line to model a clearly curved trend. It just doesn't work. Underfitting is like relying on a vague set of directions to navigate a city. You miss important landmarks and end up lost. The result is poor accuracy on both training and test data. Overfitting has some telltale symptoms. A classic one is high accuracy on training data, but low accuracy on test data. What causes this? Models that are too complex, like deep neural networks with too many layers. Small data sets that make it easy for the model to memorize examples, including noisy or irrelevant data, which confuses the model. For example, in image classification, an overfitted model might recognize shadows or background patterns instead of focusing on the actual object. Underfitting, on the other hand, has different symptoms. The model performs poorly on both training and test data, which is a clear sign it hasn't learned enough. This often happens when the model is too simple or when we haven't provided enough useful features. For example, imagine trying to predict house prices using just the square footage while ignoring location or condition. The model doesn't stand a chance at capturing the full picture. Let's talk about why overfitting happens. High model complexity. Too many parameters lead to memorization instead of learning. Limited training data. Small datasets are easy to overfit. Noisy data, outliers, or irrelevant features distract the model. Overtraining. Training for too many epochs over-specializes the model. A good example is a chatbot trained with only a few conversations. It might work well for those but fail with new users. Underfitting usually stems from oversimplification. Models that lack complexity, like linear regression for nonlinear problems. Missing important features, such as excluding weather data when predicting crop yields. Stopping training too early before the model has had a chance to learn. It's like giving a carpenter a single tool to build an entire house. It's just not enough. How do we diagnose these problems? Learning curves. For overfitting, training accuracy is high, but test accuracy is low. For underfitting, both are low and improve slowly. Cross-validation. Large differences between folds signal overfitting. Residual plots. Patterns in the residuals suggest underfitting, while randomness indicates a good fit. These tools are like diagnostic tests for our models. They help us pinpoint issues before deployment. To combat overfitting, we have a few techniques. Regularization. L1 or L2 penalties discourage complexity. Data augmentation. Generating synthetic examples helps the model generalize better. Dropout layers. These force the model to rely on multiple features instead of memorizing specific ones. Early stopping, halting training. When validation accuracy stops improving, prevents overfitting. These methods help our models focus on the big picture rather than getting stuck on irrelevant details. To prevent underfitting, we can use more complex models like decision trees or neural networks to capture nonlinear patterns. Engineer better features or add new data. Tune hyperparameters like learning rate and number of epochs. Train for longer to give the model more time to learn. For instance, adding polynomial features to linear regression can significantly improve its ability to fit complex data. Striking the right balance is an art and a science. Use cross-validation to assess how well the model generalizes to unseen data. Optimize parameters through grid search or random search. Tools like AutoML can automate these processes, making it easier to find the sweet spot. The key is iteration, building, testing, and refining until you achieve a model that performs consistently across datasets. To wrap up, here are the key takeaways. Overfitting occurs when the model memorizes noise, leading to high variance. Underfitting happens when the model misses patterns, resulting in high bias. Balancing these requires regularization, good feature engineering, and robust validation techniques. Remember, the goal isn't just accuracy, it's creating models that perform well in the real world. Thanks for your time. This is Zen Programmer. I will see you next time.